Hello everyone, welcome all on Data Phoenix webinar. Today we will speak about recommendation system, and together with us Maksym Lefarov. He is senior machine learning engineer at Spotify, and he will share his knowledge on recommendation system, how to build it and how to scale it. Also, we will have a Q&A session in the end of his presentation, so don't forget to ask your question using Slando. The widget is under the video, and we will be happy to answer to all these questions. Also, don't forget to join us on our Discord and continue discussion this topic. So I give the microphone to Max and your stage.
Hi everyone, yeah, thanks. Thanks a lot. Thanks for having me. Thanks for inviting me. Thanks for the nice introduction. As mentioned, I'm Max, and today I want to talk to you about building the internet scale recommendation systems. So I planned this talk more like an overview of an area, so I won't necessarily go into like a lot of technical details. I rather give you a lot of pointers and keywords, such that if you're interested in some specific method or some specific design idea, you can actually later on go on yourself, read about that, and deepen your knowledge as much you feel you need. So it might be much more comfortable for you if you're familiar with basic machine learning concepts. If you don't, I still think we can kind of make it work. So stick around. So what else? I designed this talk in kind of two stages. So the first, we will talk about a bit more like a theory behind recommendation systems and what machine learning methods are usually applied within the recommendation systems. And the second part is a bit more like a practical one, where we will try to sketch some design for the recommendation system just to get a better understanding of MLOps and MLCs. Right, so we will have the Q&A session afterwards, but if you still have some questions after that, feel free to reach me at LinkedIn or X. All right, with that out of the way, so what are those modern multi-stage recommendation systems and why are they actually multi-stage? So on a high level, it's quite easy to explain what recommendation system does. So you have the catalog of items and you have the user base, and you would want to match the users and the items in a way such that to maximize some specific metric that your business or your product cares about. That can be user engagement, like user satisfaction, user retention, and so on and so forth. So the complexity, as it usually happens, comes from trying to scale everything up. In the modern day, it's not really uncommon to go on the internet and interact with the recommendation system that has like hundreds of millions of items within the catalog and hundreds of millions of users within the user base. And really like going and computing the recommendation score for each pair, and it's pretty much computationally intractable. That's why most of the modern recommendation systems, they are usually built in multiple stages. And the first stage is so-called candidate generation. And the idea here is that you take your entire catalog of items, you take a specific user, and then you compute the much more reduced and feasible set of promising candidates for this user. Then we have a so-called scoring, ranking / sequencing stage. And that is where we take the user and we take the reduced set of the candidates, and we compute the kind of high fidelity personalization score for all these candidates within the feasible set. And then we either sequence them if we want to return multiple or pick the best one, and so on and so forth. And then we have a business rules stage. So this one is like slightly more vaguely defined. And here I usually group everything that kind of tries to alternate the prediction of the previous stage. We'll dive into the details about that. So don't be confused. All right. So how can we take the entire catalog of recommendation system and reduce that to some feasible candidate set? Well, one way of doing that is obviously heuristics. It's obviously not the most fun way, but usually it is quite an easy way. It is easy to implement, and it might be quite a strong baseline. So still in production, you might see some heuristics being applied to generate the candidates. And that could be as as simple as some non-personalized heuristics. For example, taking the top popular items in some user markets or demographic, or take the most recently added items. You can also go and add a bit of like personalization flavor to the heuristics and try to design something like get the shows from the genres that user has consumed recently. If you're trying to recommend the podcast, for example, or if you're trying to recommend the books, maybe give the user as a recommendation the books from the top read authors by the user. But obviously, the more interesting approach is to use machine learning. So how can we use machine learning to generate the candidates for the recommendation system? And the answer is representation learning. The idea here is that we would want to learn the vector representations for the users and the items in a specific way such that the similarity between those two vectors, like the dot product, the cosine similarity, encode some target relationship that we are caring about. For example, is the user likely to interact with the content? Is the user likely to subscribe or like buy an item? Or are two users with the similar vectors likely to buy the same product? Once you have those vectors computed for the users and the items, you can then insert those vectors into so-called approximate nearest neighbor index, or recently it's also called a vector database. And then the idea that whenever you get the request from the user and you need to generate the candidates, you basically take the user vector and you give it that to the approximate nearest neighbor. And the main task of the approximate nearest neighbor is, in a really fast time, give you the n approximately closest items in the vector space that we computed. And because how we constructed the vector space in the first place, we know that the n approximately closest items to the user are the items that the user is most likely to interact with. So that makes a really powerful candidate set that we can then later operate on. Right, so how do we learn representations? A bit of a disclaimer here. So it is actually a really wide area within the machine learning. So we actually even have a dedicated conference that is called International Conference on Learning Representations, CLEAR. And that is, I think, like either fourth or fifth largest conference on machine learning. So the space is huge. And there are also a lot of methods that are applicable in different domains, not just recommendation systems. So for somebody who is interested in learning about that, I linked the NYU lectures, and I think videos 12 and 14, or like 12 to 14, are specifically interested if you really want to learn about like, okay, how can we learn representations? And I think they're given by Jan LeCun. So yeah, I highly advise to check it out. But right, what methods do we have that can be applied specifically for the recommendation systems? Well, it all started with so-called matrix factorization. And the idea here is that you take your interaction data between the users and the items, and you construct the metrics where the rows are, for example, the items, and then the columns are the users. And you put, let's say, ones into the cells of the metrics if the user has interacted with the item. And then you can use your favorite linear algebra solver to compute the decomposition of the metrics to get the two set of vectors, set of user vectors, set of metrics vectors. That is the approach that pretty much started that all, but it has few major disadvantages. So the first one is scalability. As mentioned, we might see a recommendation system that has like hundreds of millions of items and hundreds of millions of users, and decomposing 100 million by 100 million metrics varies from really challenging to computationally impossible. So it doesn't really scale well. And the second disadvantage is that you can only use the interaction data. So in this kind of metrics factorization, you can't really add a user features and the item features, which might be quite a powerful predictors. So in order to address specifically the second limitation, the user and item features, people come up with so-called neural collaborative filtering. And the idea here is that you basically have the embeddings that are computed by the matrix factorization, so the user and the item vectors, and you join that with some with another vector that is resulted from taking user and item features and putting that through the neural network. And then you have some additional neural network layers on top. So the specific implementations and specific architectures vary, but the idea pretty much is the same. So you take the matrix factorization and you somehow join that with the processed features of users and the items to get the better predictions and to get the better vector representations. And all of that kind of culminated in a so-called two-tower model approach, which is, I think, currently is de facto a go-to approach in the industry on how to train the model to compute the user and the item representations. And the idea here is that you pretty much have like two separate neural networks, one that takes user features and they compute the embedding of the dimensionality D. And then you have another network that takes the item features and they compute the embedding of the dimensionality D. So those two networks are trained jointly in one training procedure using the contrastive learning. And then the outputs of those, the user tower and the item tower, are basically the embeddings that we are looking after. So this method has a lot of advantages behind it. So first of all, we can actually use the user and the item features. It also scales really nicely because you can do the mini batch training, how you usually train the neural network. So the huge data set is not really a problem, as long as you have enough computational resources. And then what's even more interesting, that those two networks, like the user tower and the item tower, once you train them, you can actually inference them for the users and items independently. So if you're in a situation that your item catalog is changing all the time, for example, and your user base is changing all the time, then you don't really need to retrain like everything all together once you have the new user to compute the embeddings. You can just take the user features, inference the user tower, and get out the user embedding. Right, but yeah, industry is not like staying on one place, so it's also moving. So recently I've seen a new and more advanced architecture popping out here and there, also being deployed in production. So one of these architectures is graph neural networks. And the idea here would be that you can think about recommendation and interactions between the user and the item as a graph. So you have the nodes in the graph that represent the users and the nodes in the graph that represent the items. And you can, for example, draw the edge between two of them if the user has, let's say, streamed the item or like bought the item, whatever you have in your product. Once you have that, you can actually apply graph neural network to compute the embeddings. And there is a Medium post by Pinterest where they present PinSage. So that is their graph neural network-based architecture to compute the embeddings. And also in Spotify, the tech research department has recently published a paper. They haven't yet written a nice blog post to really explain the paper to somebody who doesn't really read scientific publications. But the idea here is that they used graph neural networks to actually bootstrap the recommendations of the audiobooks. So if you're interested in this kind of approaches, if you're interested in graph neural nets, I think that would be like two starting points to look into. But then also there is a new most popular model in town, which is the transformer. And I think people started talking about applying transformers to recommendations like as early as probably like 2019 or something. And from what I've noticed, NVIDIA was quite early in the space with their idea of look at the recommendation as the sequence modeling problem. So you have the user that interacts with item A, item B, item C. So you can really represent this sequence of items as the sequence of tokens, let's say, and then you can use the sequence model to predict the next item. And they propose to use transformer for that, obviously, because transformer is really nice and scalable architecture. I think it still had some problems because serving transformer in a real-time high-scale recommendation system to do this, what one might call zero-shot prediction of the next item to recommend, might be a bit problematic. But the good idea and the good thing about transformers is that apart from generating tokens, they also can generate really powerful representations of the tokens, right? That's how we train transformers in the first place. We compute the embeddings for the tokens, and then we can use those embeddings for the different tasks like classification, regression, and so on and so forth. So you could think about using transformer to compute this joint user and item representations. Sorry. Right, and I think the latest paper in this direction comes from Meta, that is called "Action Speaks Louder Than the Words." And the idea there is that they actually propose to build a huge transformer that would operate on the text plus the items of the recommendation system. I think in their case, that would probably be Facebook. And then you can, again, do the zero-shot recommendation. You just pretty much like input the prompt in a text. You append some items that the user has interacted in like past 10 minutes. And then you forward that through transformer and you get out a next most probable token, which ideally should be the item that the user is most likely to engage with. All right, yeah, it was a lot of talking from my side. So I hope I didn't confuse you too much, but I put the links here and I will share the slides. So if you want to read, more about one of those specific things, you can just go ahead and do so. But yeah, time-wise, I think we need to move on. So the next stage is scoring, ranking, and sequencing, or what one might call it fine-grained personalization. So the idea here is that now you have the candidate set that is greatly reduced, and you would want to compute an actual personalization score for the user for each item, and then select top N candidates. And that is the range of supervised model data that's still quite small. So within the industry, I usually see still a few layer neural networks. And that is basically because we are still trying to optimize for latency at this stage. So going really big and crazy might be problematic. This stage usually focus on putting like even more features that are usually also some contextual features. For example, what type of device user is using if you have an application on multiple platforms, or more reactive features, like the features that can really alternate the prediction based on the recent user activity. So for example, the time since the last interaction, or the click-through rate of the user within 1 hour, one previous hour, or something like that. And then we have kind of a business rules where I usually group everything else that did not fit into 2 previous stages. And here we can think about implementing some rules or heuristics to ensure some specific outcomes that might be required by your product team or by business, such as, for example, content balancing. So if you're building a platform where you have multiple contents, you might need to make sure that every type of the content show up not least than 30% or something. Then you might also think about repetition capping. So this one basically to prevent the user see the same recommendation or similar recommendation within the time span, not to exhaust the user attention. You can think about safety and sensitivity checks, and also non-organic content recommendation. So that is basically blending in the recommendations that are not driven primarily by the metrics that you've optimized for, but also some other metrics that your organization is caring about. I think the most relevant example might be something like ads. Obviously, all of that ideally can be included into the previous stages, so that you might, you might construct your modeling task around accounting for all these requirements. But nowadays, recommendation system, they've grown significantly, and also grown in complexity. So really, a lot of people still prefer to just put that as the final filter at the end, because changing something in the previous stages will require a lot of testing, a lot of cooperation, and also it's not as easy to pull out. Of course, everything depends on the scale you operate on. So yeah, pretty much pick your poison. All right, so that was like a bit of a theoretical part. Now we'll look more into practical side of things. And we'll try to do that by building a dummy architecture for some dummy recommendation system. So yeah, the caveat, all of that is obviously not super optimized. There are a lot of assumptions. But again, my idea here is not to give you the best architecture for a specific recommendation system, but rather give you some pointers you might want to think about when you're trying to build the recommendation system stack yourself. Okay, so let's assume you've been hired to some company that has a client application that might be an Android app or iOS app that has some UX items, and your task is to build a system that would decide which recommended content for a specific user to put in the first place in the homepage of this application. So what happens when user pulls out smartphone, goes to the homepage, you send the request to the backend architecture, and then depends on the complexity of this backend architecture, this request might jump a few microservices, but sooner than later, this request will hit your backend service that drives recommendation system, and it will pretty much ask what should we put in the position 1 for this specific user ID. So that is where our job starts, and we already have a major design decision to make. And the question is, do we want to go with the batch inference or online inference? And the batch inference here means that we don't really compute anything on the user request path. What we do is just look up previously computed results from the storage system. Whereas online inference means that whenever we get requests from the user, we'll actually do the computation of the result. That would involve most probably inference in machine learning model, applying the business rules, selecting the winner, and sending it back. So before we even think about what are the technical implications of our choice, we should have a really good conversation with the product team, with the business team, with the UX team, and ask pretty much like the following questions. So are we okay with the fact that the content recommended to the user will be stale? And stale here means that basically whenever a user will come to the homepage repeatedly several times, he or she might see the same content. And that is driven by the fact that we don't recompute anything on the fly, we just fetch the solution that were computed previously. How do we schedule our inference? So how often do we recompute the solutions? And what should we do with the new users? So there could be a situation when some user comes to the platform and you got the request knocking on your service door, but you don't really have this user ID in the storage. So what should you return then? But let's assume that we took that up to discussion with our product team, with our business team, UX, UI, and so on and so forth, and we decided that all of those questions are not the blockers, and we can actually go with the batch inference. Yeah, and that's why we probably should start with that, because batch inference eliminates like few challenges from the architecture, and it's might be considered like a bit easier. In general, I think in software engineering, it's kind of a good practice to start with the easiest solution first. So as mentioned, whenever we get the request, we won't recompute anything on the fly. We would actually go to the some storage system and get back the pre-computed result. And I think the industry jargon for that is curated result. So few consideration of what type of storage we should pick. First of all, we don't really need SQL. we're just interested in a simple key value lookup. So given the user ID, get the previously computed results. We are interested in the storage system that is optimized for the high throughput reads. And then we're also interested in all the things that are related to the system design, like high availability, eventual consistency, and so on and so forth. So here are a few options you might want to consider. And just a disclaimer, obviously there are like a huge amount of options nowadays for every tech stack. Those are just things that either I used or have read about or know the people that used. So that is definitely not the full list. And you obviously could have a solution that is drastically different. But in any case, if you host on Google Cloud, you might use Google Bigtable that is designed for exactly this use case. If you host on AWS, you may try DynamoDB. Or if you want to, get your hands dirty and kind of try to build everything a bit more by hand, or you want to have like more configuration capacity, then you might think about spinning up Redis cluster. Right. So in order to get the results from the database, we also need to put the results in the database. And for that, we would need to have the batch inference job. And the task of this job would be to take the machine learning model that we built, take the users, take the items, compute the predictions for each user item pair, for each user select the best item, ingest into the database. And we'll talk about the batch inference job more in detail later, but anyhow, in order to actually do that repetitively, you would need to schedule this batch inference job. And thus we need the scheduling service. And some considerations we might want to have about the scheduling service is that we would probably want a distributed job execution. We would want some dependency management. And here by the dependency, I mean, so if you think about that, your batch inference job would consume some machine learning model, but to get the machine learning model, you need some training job to actually produce the machine learning model. So in essence, your batch inference job actually depends on your training job. And you would want to use the scheduler that allows you to specify those kind of dependencies. And of course, you also want to have some kind of fault recoveries to make sure that if one of the job execution fails, it just doesn't take down the entire architecture, but the job is retried, or when it's retried and failed more than specified number of times, it sends to page to maintain the team. So yeah, all the good stuff that is applicable to any system engineering. So what are options we have? So we have Flight. That is a framework for doing exactly that. That was originally developed by Lyft and then open sourced. Then we have Luigi, another framework that was developed by Spotify and then open sourced. And then if you're hosting on some cloud, just go to the documentation of your cloud provider. I'm sure they have some cloud-specific solution for you. All right, now let's switch gears slightly and talk about data in the model. Yeah, as I hope you guessed by now, an actual like modeling problem is really like kind of a small part in all this building end-to-end recommendation system business. So I don't really want to go into like thinking about complex model architectures and stuff. So here we'll just say that we have a simple few layers feed-forward network that takes the user features, that takes the item features and predict whether the user will engage with the item. So you basically model that as a classification task. So for that, you need the training job. And for the training job, you obviously need the training data. So let's assume that the other backend or front-end engineers already implemented the system to stream the interaction logs from the client into some persistent database. So basically, you would have a database somewhere in your stack that would store the events of user A has clicked on item B, like user B has streamed item A. And you can use those events as the backbone for your training data creation and evaluation data creation, and then just join the user features and item features to that. But before you do that, there are a few major considerations to make. And actually, to be honest, like the data topic, I think it's one of the most complicated within recommendation systems. That's why also often in big companies, they actually separate the data engineer role with the machine learning engineer role, because it's just, there are so much things to keep in your mind, and that are not necessarily related to the machine learning itself, or like to model development itself. So it makes sense in some big organizations. But in any case, one thing you definitely need to consider is to how to collect the unbiased data. And the idea here is that, especially if you have already closed the loop, and your recommendations here are powered by, let's say, the previous version of your machine learning model that runs in production, and you wouldn't want to build a new model or retrain the existing model to make sure that it's up to date with all the data shifts and so on and so forth, you need to make sure that you are collecting the data that is not biased by your previous model. And by biased, what we mean here is it's a bit kind of difficult to explain if you never worked with that. And I think you can also just go in Google. There are probably a lot of good blog posts that explain in a better terms that I will try to do here. But the idea here that you have a data space which represents like all possibilities between users and items. And if you collect the data, when your recommendation system decides what to show to which user, you basically shift the distribution of all possible data in the specific region of this data, a specific region of this data space. And that's what makes your data biased. And it's, it has a lot of bad implications. And I think you can actually really just, would be really nice if you just go and read about that if you're interested, because it would just take way much time if we would discuss all of that. But in any case, anyhow, you need to find a way to do the unbiased data collection. And there are few possibilities you might consider. The easiest one, which I'd say like 90% of people decided to go with, is just the random data collection. So the idea here that every time you got the request from the user to your recommendation service, for the fixed chance, like 5% or something, you'd actually give out a completely random item from your catalog, not influenced by your recommendation stack. And that will make sure that when you collect your training data, if you only take those items, if you only take the records, the interaction facts that include those random recommendations, your data will be unbiased. Another way to make sure that you mitigate this bias problem is to do a specific unbiasing techniques, but those are a bit more complex, and usually people do that only when collecting the random data is kind of like no optional hard sell. So for example, if you are trying to build a recommendation system to recommend in like some paid content, like for example, ads or something, it might be a hard sell if you go back to your stakeholders and say that, oh, well, to train our model, we would need to send your ad that we promised to send to the most relevant users. 5% of the time we'll send it to the random users just to train our model. It might be problematic. But in any case, in our case, it's not a problem, so we'll just go with the random data collection. The next point you want to consider is the labels attribution. And again, that is like kind of a big subspace, and usually data engineers and backend engineers are thinking about that. But in our simple system, that basically means that we need a way to join the interaction logs that we have here with the logs of the recommendation system. And that is to make sure that we can actually select the random data to build our training and eval set. And there are different ways to do that, and they all vary in complexity. But for the sake of example, let's say that we will try to do that by persisting the request ID. So whenever we send the request out to our recommendation system, which is like not visible here, but imagine it's there. Whenever the recommendation system computes something for this request, it logs whatever it needs to log. So in our case, for example, whether it's being treated as the random request or not, with this request ID. And then it returns back the request ID. And then the interaction fact is also logged with the request ID. So you can actually just take the interaction logs, join that with your recommendation system logs, and only select the data where you have the random serving to make sure that the data is unbiased. Another big topic is feature and labels, feature alignment and labels leakage. And this one is, again, quite problematic and like huge topic in itself that probably deserves like a dedicated 40 minutes lecture. But the way you might want to try to understand that is when you collect your training data from the interaction facts, in order to collect enough training data, you probably look like quite some time into the past. Let's say you want to aggregate the logs over the last months. And all these interaction facts, which is literally like the pair of the user ID and the item ID, you would want to join the features to that. But you need to make sure when you join the features that whatever feature you've joined is never using the information from the future. And then might sound silly, like duh, yeah, I mean, it's easy. But whenever you have some really complex features, they do, which, for example, do some pre-computation or like some feature aggregation and so on and so forth, it's quickly becoming not as trivial as you might think. That is why it's like the entire subfield of data engineering, where people build a system to make sure that whenever you join the features to like backbone interactions, it's always without leakage, it's always with the correct partition, it's always with the correct time step. But in any case, with all that out of the way, so we kind of come up with pretty much the design decisions we would want to use for all those problems. Now we can actually build the training data aggregation pipeline. So what stack should we consider for our data? Well, a few things. We definitely need joins, because we have this interaction pairs and we would want to join the features. And we also need the map reuse. And that is to maybe compute some more complex features, like do the feature aggregations and so on and so forth. So what options do we have? Well, if we're just starting and like system is still quite small, scheduled SQL queries might do the job. But as you scale, as you move into the future, looking into dedicated frameworks such as Apache Beam or Apache Spark makes total sense. Right, now we kind of has closed the loop from the logs to the training data to the model. And now we can finally look into what's happening within the batch inference job, because there are still a few interesting technical challenges that we would want to address. So in the easiest possible case, your training job is just, sorry, not training job, no, batch inference job. Sort of confusion. We're looking into batch inference job. The training job is actually like the easiest part of the puzzle, just some script that takes the data, train the model, offload the model. But the batch inference job is where some new interesting problems might arise. So in the batch inference job, in the easiest case, you just have an inference script that takes the model, takes the users, takes the items, computes the predictions, takes the best item for the user, ingests that. So the stack here really depends on what is the time frame to compute the inference. So how often do you want to recompute the inference, and what is like the maximum allowed time to do that, and the scale of your data set. And if you've done some experiments and you can see that actually, let's say you have 24 hours to recompute the inference because you would want to update the results every 24 hours. And you've seen that with the size of the data set you have, you're actually good to go with a single machine. Then you're good. You can use either PyTorch or TensorFlow, or pretty much anything else like scikit-learn. The only thing you might need to consider, or like the thing that you definitely need to consider, is that you would actually need to have a data streaming, because even if your data set is small to be processed in time on a single machine, most probably it's not small enough to fit into RAM of a single machine. So you would need to either use something that is already provided by the PyTorch or TensorFlow, which is good, or you might need, if you're using some obscure framework, you might need to raw dog implement it yourself using something like PyArrow or similar technology. So what to do if a single machine is not fast enough and you've tried the vertical scale and you reach the limit? Well, then you can do the horizontal scaling, basically run that on many machines. To do that, you have, again, multiple options as everywhere. First of all, I would look into the Ray framework. So this is nowadays really popular framework for doing distributed computing that also has a lot of libraries specifically for doing machine learning. So it's really kind of a safe bet. Another thing, especially if you already decided to run your data pipelines on Apache Beam, you can actually use Apache Beam to do the inference, because Apache Beam has implementations in multiple languages, including Python. So you can specify your logic in Python and you would have the access to Python interpreter. So you can actually load whatever TensorFlow or PyTorch model on every machine that does the inference and actually, pretty much do the inference, but in a distributed fashion. highly scalable. Okay, that's all good, but I hope that you see a problem here. And the problem is that our computation scales as a product of number of users and the number of items. And even if you do the horizontal scaling, at some point, it still becomes intractable. And here I hope that there is a bell ringing in your head saying that, well, we know what to do. We need a two-stage recommendation system. So we need to limit somehow the number of items that we consider for inference for each user. One way of doing that, of course, would be, as we discussed, trying to come up with some heuristics, which is the good first step. But just for being a bit more like considerate of the time, would actually go directly to approximate nearest neighbor approach. And the idea here would be that your inference script for each user, it queries the NN index and asks for n items with the closest vectors to the user vector. And then you do the inference only for that. So for NN itself, there are multiple options. So you can use some NN-specific software, like, for example, NNOI, which stands for Approximate Nearest Neighbor, or YES, that was originally developed by Eric Berhanson at Spotify and then open source. And I also actually linked the original blog post by Eric, which describes how actually ANN is working. That is like only a single way to implement ANN. There are multiples, but it's really nice read. So I definitely recommend that. Then you have the reincarnation of NOI, which is Voyager, which is also was developed by Spotify and then open source. You can go to a bit more like a heavyweight solution or like integrated solution. So for example, Elasticsearch has the approximate nearest neighbor. And again, you can go back to your cloud provider and ask for any vector database they might provide you with. So it will pretty much work. Now, that is the good thing. We've reduced our amount of the computation that we need to do. But obviously, there is a drawback. And the drawback comes in the form of additional complexity. So to have the embeddings, you need to have the model that computes the embeddings. And for this model, you need to gather the training data, you need to implement the training job, you need to implement the inference job, right? So new model, additional complexity. Well, the good thing about that is that we can draw the line and say that all this complexity should be taken care of by another team. That might sound silly at some point, I understand, but it actually kind of makes sense, especially in the bigger organizations. And it makes sense because the way you would want to train this, in our case, I've picked a 2-tower model, and that can be any embedding model. The way you would want to train that is not necessarily the same way you would actually want to train the personalization model at the next stage, the one that we've been trying to train. You might want to use different data from the different part of the application. You definitely have a different architecture. You might want to have different hyperparameters. So a lot of different things. And this model that computes the embeddings, it can actually be also reused by multiple recommendation systems. So now we talk about building a recommendation system to recommend the content on the first place on the homepage. But there could be in the future another recommendation system that, for example, powers search in the application. And then this new recommendation system can also use this embedding model as the first stage, as the candidate generation model through the approximate nearest neighbor index. So it makes sense to actually dedicate engineering resources directly to building and maintaining this solution. All right, that is the final overview of everything that we've engineered so far, or like designed so far. So you have the full loop going from logs to training data to model being inferenced, the batch job being scheduled, all the jobs being scheduled, ingesting the curated results, and then the backend service on the user request, fetching those results and serving back to the user. All right, I think that was enough of me rambling here. I hope I didn't confuse you too much, but yeah, if you have any questions, please go ahead.
Yeah, thank you for this cool overview and help to all understand how a recommendation system works. Continue this, your talk. I have additional questions about, okay, we have this system. Now we go to the production. First question, what should we monitor and what metrics we need to, on which metrics we need to look first to understand that all is going good?
Right. I think there are two sets of metrics, like two classes of metrics. One is the product metrics designed by your product people and the data scientists and statisticians, which basically track some top level metrics, right? Like, for example, user churn or user interactions or some form of user satisfaction. So you need to make sure that you're not tanking these metrics. And then you also have, obviously, well, it's not like you obviously have, but it's nice to have tracking of the metrics for training job. So whenever you retrain the model, if you have this process scheduled, if you have the automatic retraining of the model every day, every week, etc., you can also compute the usual machine learning metrics that you have for a specific task. So for example, if you train your model as a classification, you might look at the accuracy on the eval set and the IUC ROC, IUC PR. And whenever you train the model, you can run the evaluation alongside on the eval set, and you can record and monitor all those metrics just to make sure that there is no degradation. If you see degradation, maybe you need to tweak the hyperparameters. Maybe you need to think about ingesting more data. So yeah, two classes of matrices, the product one and the classical machine learning metrics.
Yeah.
And I think also backend engineers will jump in here and say that for the part of the stack where you kind of wrap everything with the backend service, you obviously also need to track like all the latency, P99, like the uptime, and so on and so forth. So it will quite quickly become a huge amount of metrics somewhere in Grafana.
Yeah. And also when we have some metrics, how to better to validate that our system, recommendation system work correctly? Maybe we can use some specific tools.
I mean, usually you validate that by having a baselines on your metrics and then making sure that you are not underperforming the baselines, or you benchmark your current performance against the past performance. So if you do the training of the model like with the regular intervals, you check that the metrics do not degrade. You also look at the product metrics, something like user churn or like average user click-through rate, and make sure that it's not tanking or like not going down. And in terms of software, I think for machine learning particularly, there are a lot of solutions. So there is the MLflow framework, there is a weights and biases framework that actually allows you to hook into the training process and evaluation process, record the metrics, and basically visualize and sort that centrally, so that everyone can then, even if the model train was triggered automatically and you have the training going on, you can just go to the dashboard in weights and biases and MLflow and check, okay, you can look at the training loss, you can see that in the eval loss, see that you don't overfit. You can check the AUC PR or AUC ROC of the previous training runs and so on and so forth. And for the product metrics, how those monitored, I'm not sure. I think you need to talk to somebody who is more like into data science, maybe some kind of Tableau, I'm not sure.
So, some like Amplitude or something, tools which product men use for their work. Yeah,
probably.
Yeah. Okay. We have also part for validation. Now we want to update our models in production. What is the best strategy to not interrupt user services and update our models in the recommendation system?
That depends on whether we are talking about update as about like trying something new with the model. So for example, you would want to add a new feature, you would want to change the architecture, you would want to change the training data collection somehow. If that is this kind of drastic change, then the safest bet is to go with the A/B test. So you would want to do the A/B test where the control cell would be your previous solution, and the test cell would be something that you build. If you're talking about updating model, like retraining model with the regular intervals, that is commonly done to make sure that the data shift does not bite you, then I think you don't really need as drastic situation as drastic measure as the A/B test. You can just, again, have the script that is scheduled, let's say, every week or every day to retrain the model on the new aggregated trained data, and then closely monitor the metrics in MLflow, like weighted biases, to make sure that nothing goes really bad. And if something goes really bad, page some engineer who is on duty to make sure that everything is rolled back. But yeah, that's pretty much the gist of it.
Yeah. Okay. You start to speak in the beginning of your presentation about transformers. How do you see that LLMs can change the recommendation system and how they can improve it?
Yeah, that is like a difficult question. I think it's like really active area of research, and a lot of people are looking like in all directions that are related to this topic. I think the interesting opportunity area might be, but again, like I'm not a researcher, right? And take it with a grain of salt. I think interesting opportunity might be in like doing recommendation system with a bit more like text UX. So the idea that you would have the model that understands the user queries, but it also understands or knows about your the items within your recommendation system, and can directly output the items given the user queries. So that would, I think that's what the Facebook or like the Meta paper that I linked is about, and a lot of people think that might be a really promising direction to replace all this multi-stage stack with the single sequence model or language model that can just either take a query from the user or just take the user history or something, then in one shot output the next recommendation. There are a lot of open questions with that. Like, obviously you don't want, especially if your application is like quite big and you've accumulated a huge amount of data, you don't really want to lose all the data and just replace everything with like LLM doing one shot. So you probably want to use this data to like either fine tune or modify the LLM. But there are also like a lot of open questions how to do that. Yeah, a lot of
yes. Some of the way it's to use something like RAG and then to have the vector database where you store all your data and do some semantic search on the RAG and then get from it some recommendation. But it's very interesting area which are only start to growing, and we'll see what will be created in this area. Okay, we have some questions from our participants about slides. We will share with you link. Please don't forget to join Discord, where we will share the video and also the presentation. Interesting question about temporal dynamics of data, something threads, news, and use it in recommendation system.
Right. So there are like a few ways if you have pretty big application that is like a platform like Facebook or Amazon or Netflix or Spotify, you might observe those trends, like more general trends, industry trends within your data itself, because those trends obviously influence how user is behaving, what users are searching for, what users are streaming, what users are clicking. So if you have powerful features enough that are built on your data, you might explicitly account for those trends. But it's not uncommon for big recommendation systems to actually go out and source the data from the outside that are related to the trends. I think there are a few startups or maybe even established companies who actually built around that, kind of analyzing the trends and then providing that as the data, like near real-time data to other companies so that they can use that as a feature in the recommendation systems. So that would be another solution. Really depends on what you're building, what is your scale, if you can observe the general trends in your data already. As usual with all of that, I think the majority of my questions would be kind of depends, but it's really induced by the fact that it's a huge area. It's really difficult to give like a specific example, a specific answer without talk in specifics about the problem.
Yeah. Next question about cold start problem. So you told about this one, but what is your best way to solve this problem?
Right. This one is like really kind of really known and really big also in the recommendation systems. It might be about the new users about which you don't know anything, or new content about which you don't know anything. So with the content, it's slightly easier because you can, I think you can usually have pretty strong content features, like content only. So if you have the new content on your platform, and for example, your platform is about recommending books, you can just take the transcript of the book and then, for example, put that through the transformer, and you would get some embedding that is already a powerful feature to mitigate this cold start problem. So if you use this feature in your actual model, that might help you quite a bit. The same, for example, with the video, you can put video, let's say, through the transformer or some other signal processing solutions to get some form of the feature. It usually gets more difficult when we talk about the users, because for the user, the most powerful, there is no such thing as the really powerful content feature for the user, if you know what I mean. So usually the most powerful user features are actually the interactions data, right? So the embeddings for the users that we can compute from the interactions data. And if you don't have any interaction on your platform for the user, obviously it's a bit problematic. But people address that in multiple ways. I think one of the way, maybe straightforward way to do that is to do exploration, so-called exploration. So the same thing that we did to collect the unbiased training data, where we just randomly send some random items based on the chance. We can also do that for the cold start users. We could just randomly send the items, but then we need to make sure that our loop, which goes from the training data to the machine learning model, actually operates with a really fast cadence, such that we don't really spam the new user with random experience for a week until machine learning model picks up what user likes, what user doesn't like. But we have a more, kind of more fancy solution where you can pick it up much quicker. And usually that would involve doing maybe some Bayesian inference to update the user vector in near real time, or maybe you can do the bandits to minimize the number of random servings for the user and try to infer the user preferences as fast as you can. But you can also solve that on the product level. So I think pretty much with every problem, you can also think about how you can solve that with the product. So, you have an application of recommending the books, and you have the user registering. You can just display as a first screen to the user, okay, what books do you enjoy reading to, right? Would you like to read about that? Would you like to read about that? And you can already use this information that you artificially sourced to actually warm start the user. So really, as usual, a lot of things.
Yeah. Next question: what your way on trade-off between using complex recommendation system model and inference latency for online inference?
Yeah, especially for the online inference, I think from what obviously I might have not the entire overview and stuff, but I'd say people don't really use fancy model, especially if we talk about online inference. Because remember, when you do online inference, whenever you get the request, you would actually need to first you would need to join the features that you previously probably ingested. So you need to get the features for this user, and then you need to go to the approximate nearest neighbor, get the best items, the most probable items. Then you need to join the features to those items, and then finally you need to send all of that to the machine learning model to compute the prediction scores. So latency here is really following the strict latency requirements is tough, especially if you consider the fact that if your application is big, the request before actually hitting your service, it might already jump multiple services that can also do quite heavy lifting of thinking about how to decorate the content and so on and so forth. So really, we're talking about yeah, milliseconds of latency. And usually you try to go with like a smallest model you can. If you have a really good reasons for like going with a big model with a lot of parameters that is heavy on inference, then obviously you need to think about optimization techniques. You need to think about the caching for the inference itself. You need to think about maybe like quantizing your model, maybe developing some specific like low-level implementation of the model so that you can serve it like really fast. So yeah, everything is trade-off. But from what I see, like unless you go to the transformer and you have the amount of data that you can kind of crawl the web, like trillions of data, it doesn't really like make sense to bloat your model like to the huge amount of parameters. It's always good to start small, and given like looking at the amount of data, small fully connected model can already give you good performance, and then you can iterate out of that.
Yeah, it's like better to use a lot of different small models and do orchestration of them and correct routing, which model for which situation to select.
I like that. Yeah, that's another option. That's true.
Yeah. Okay. Other question about organized model training and your experience with real-time training.
I'm not 100% sure what does real-time training means, but yeah, obviously, like organizing model training. Yeah, I don't really know like what is real-time training, but I assume that you have just you have the training logic that you need to implement, and that can be as simple as having like a simple, let's say, PyTorch-based Python script that is then scheduled with your scheduler to execute every hour, like a day or week or something. Or it can go as complex as using some specific model training solution, something like, for example, TensorFlow, they have an extension that is called Kubeflow that actually allows you to express your model training pipeline in multiple stages, like with feature preprocessing, with model training, with the hyperparameter optimization. And if you express that in the TensorFlow as the pipeline, not TensorFlow, Kubeflow. If you express that in a Kubeflow, you can then make sure that all those stages are running on the Kubernetes nodes like independently, and it's highly scalable horizontally. So if you need that, you can also go with that. But I think especially like at the beginning when you're thinking about the first prototype, Python script with PyTorch with data streaming to train the model and then ingest it in some blob, it will do.
Mm-hmm. Yeah. Next question about what your experience with learning to rank family of models.
Learning to rank family of models. I'm not sure I'm familiar with that, at least with this term. Learning to rank. No. I'm not sure what people mean by that, to be honest. Learning to rank.
Okay. We also have the comments about what's mean real-time training. It's something like monolith for bited dates.
ByteDance. Real-time training would be just like monolith ByteDance. Is it like about like training model as soon as you get some new training data and not waiting for like specific intervals? So basically, let's say your users are constantly interacting with the application. You stream the logs, like save it somewhere in DB, and then you have logic that says, okay, as soon as we collected like 5K new samples, we will train the model. Or is it more about like the model architectures that can be updated real time, like the Bayesian models, where you can take the prior and you can take all the data that is like you just observed a second ago and then compute the new model? Depends. Depends what you mean by real time. So I'd say if you really want to go after the real time, you probably need to do some Bayesian style updates, which obviously is getting way more complex like immediately. So if you can fake real time by just retraining your model more often, like having this kind of some maybe weird or a bit hand-tuned logic of like retraining the model as soon as you have like some some chunk of new available data or something like that. Maybe that's a better way to go. If you really want to go like full real-time experience where your model is basically you have the new instance of the model, like whenever you have a new data, then I can only think about Bayesian updates or like Bayesian-based models. Complex. Need to have really good arguments to do that, I think.
Yeah. Next question about how do you address feedback loops problems in your models?
Right. So that is like exactly another name to the biased data problem. So the idea that if you let your model recommend things to the user, and then to train the next iteration of this model, you actually use this data. That means that the previous iteration of the model induced the training data that is used to train the new model. So you have a kind of a feedback loop, which is obviously not good. And again, as mentioned, there are a few ways to do that. Random servings for the fraction of the users. It's the easiest and kind of works. If you have some really strict product requirements that does not allow that, you might think about like some debiasing techniques, but it's you always pay with the cost for that, because then you would need to let's see, I think you would either need to modify the training procedure, or maybe the way you collect the data would be a bit more involved. So yeah, if you can probably just go with the random data collection and then train on the random data and evaluate on the random data.
Mm-hmm. Yeah. Next question about metrics which you use for evaluating with your team, and does offline evaluation transfer into online performance in your case?
Right. Yeah, that's always dependent on the tasks that we solve at hand. Really, offline metrics that are usually just the classical machine learning metrics that you evaluate on the eval task. So that again, for classification, that could be accuracy or what's the name? So I forgot. Area under the curve for RC or ROC, for the PR or ROC. If you talk about ranking, that can be MRR, or like recall at something, and like recall at 30 items. And then online metrics, that's what you see, like the product metrics you see actually during the A/B test. If you, for some reason, decided to skip the A/B test, the product metrics you see once you deployed the model. And then the question is whether those correlate. Not always and not necessarily. So that's, I think, the big problem, especially in a more complex recommendation system, when, for example, you have a team that builds a model for a specific type of recommendation somewhere in application specifically, but then the response from the model also goes through some post-processing that your team might not control, for example. Coming up with like offline metrics that actually correlate pretty well with the online product metrics that you are actually caring about might be quite challenging. So, and that's why most of the time as you start to scale, it's a good idea to invest into experimentation capabilities, like maybe some experimentation platform, centrally managed, to streamline the way you do the A/B testing. Because with all of that, I think A/B test would be the ultimate arbiter to decide whether to deploy something to production or not.
Yeah, and next question about how good are pure content-based recommenders?
Yeah, that is a good question. Depends on the context, right? That's probably better than nothing. But ultimately, I think the pure content-based recommendations, the best thing, so let's think about that. I think if you think, and if I'm not mistaken, the best thing you can do with the purely content-based recommendation is to discover the global popularity of the content. So you would have your items, and for each item, somehow you basically compute if you give this item to an average user from your platform, or like to all the users on the platform, whether it will be streamed or like consumed or clicked a lot or not. And that is, I think, the maximum you can achieve. You can achieve without including user information, without doing any personalization. So if that's enough for your product, because it always like really initiates from the product side. You build a recommendation system not to just send something to the user, so impress your friends or something. It usually goes from the product requirement. So you need to solve some specific product problem, and then based on the product problem formulation, you can think about, maybe like given the product formulation, it's all right. Like maybe you just want to identify the, let's say, top 100 globally popular items within your catalog. Then building a recommendation system that actually identifies those top 100 globally popular content and serves them back to the user is a good solution. So always depends.
Where do you draw the line between search and recommendation?
Oh, that's such a good question. I think the line is so blurred. And actually, like in one of the blog posts that I linked from Google about two-tower model, it's a real nice blog post where they walk you through like the evolution from matrix factorization to the two-tower, but they really like use the recommendation with the search like interchangeably, and it's really difficult to to sometimes parse what's going on. But the idea is, at least in my head, I think about search when I have the user query. So when I have the textual query from the user that specifies the user intent, I would say that's search. Whenever I have just, user does not specify an intent, it just opens an application, or it just looks somewhere on a web page and you need to fill some space, within some part of the web page, but there is no user query specified for you explicitly, then it's probably a recommendation. But a lot of methods are like extremely similar, and a lot of systems you would build for the search and for the search and recommendation are quite similar. With the caveat is that for search, whenever you think about sourcing the candidates, about this first stage where you take your items and reduce them back to the reasonable subset, you would also want to exploit the method that allow you to, to consider explicitly the user query. Because if user searches for some specific name of the book, but you just output the books that are like semantically similar to the book that user searches for, or like semantically similar to the users, that's probably a bad system for search. So you need really to consider also what user types in the query. So that would be my line, but it is really blurred, I'd say, and it's difficult to draw the line.
Next question: do you use multi-arm bandits in your system?
Yes, we do. And for the cold start of the users, yes.
And two more questions about LLMs, fundamental models, and all this stuff. So first, it's really think that will be some fundamental model for recommendation systems like we for now see for NLP and time series forecasting.
That is a really interesting question, and I'd say that would be really exciting. I think I don't know, like really difficult to predict, but as I see, one blocker for that happening might be the fact that we have like private companies, like corporations, that have a lot of data that they don't really share the data publicly, right? And in order to build the foundations language model, people actually had to crawl the entire web of data and really source like a trillions of tokens. In this case, like token is the data point. And even if we have this amount of data, clustered or scattered around different organizations, in my head, the probability of the event when people like come together, like pull all this data together and then train one like mega model to be the foundational model for recommendation, like in all domains, probably chances of happening of this thing happening is quite low, just because of the corporation would want to protect their modes and their data, because the data is the mode in this sense.
Yeah, but it's, in this case, it's possible to use some fundamental generical model and use RAG, which will use for specific data for this model. And the last question, it's why we need to choose, I can say, traditional models or better to use RAG system.
But with the rec system, like what exactly? I think the question of what the person means by the rec system in this case, because I'm familiar with the rec system in terms of doing the the language tasks, where you have the documents embedded with the language model saved in the database, and then you have the user query, and then you embed that and search for the documents that are like closest to this query. But that's pretty much exactly what we do with the recommendation system, right? We just don't call that rec, we call that multi-stage recommendation system. So you have some model that you train that embeds the users and the items. You get the user, you embed it, you know the vector of the user, you go to approximate nearest neighbor, which is also, I think, part of rec. And then you ask for like, okay, like just give me like n items that are like closest, the best match for this user. And then you can take it from there. And yeah, so I'd say like the stacks are similar. So I don't really know like what the person means by rec in terms of recommendation system. But to the retraining part, I think you need to retrain like everything because also if you think about your application, that might be induced by your application, but obviously the data shifts, the user behavior shifts, everything changes, everything is dynamic. So you can't really go with like training a single model and then living with that for the rest of the life of the application. And usually what people observe, like the faster you retrain, the easier for you it's to pick up on like recent trends and deliver better recommendations. So that's why we retrain the models.
Yeah, I think the difference between multi-stage recommendation system and RAG, it's the models which in the end use it in these systems. So in the RAG we use something like LLMs. In multi-stage model we use some, I can say, classic machine learning model. But it's very similar design of the system, how all is work.
Right.
Okay, yeah, and last question about how do you see the future of recommendation system? Where all will go?
I have no
Your
idea.
prediction.
I mean, what I would like to have is obviously more personalization capabilities. So I think right now we already have systems that are able to recommend you content quite good. So if you go to YouTube and open the homepage, a good chance that you will get a recommendation that would satisfy you at the end. I think the same with Spotify, but I might be biased. Usually when I put Spotify like in the radio mode, I kind of always satisfied with, well, like, most of the time I'm satisfied with what play next. And I think like Amazon recommendations of the next product or similar products are quite good. But I think what I'm looking more is recommendation systems that are that are more capable of understanding like more narrow user tastes. Because in the recommendation system that we see today, we still have this what we might call a popularity bias. Like imagine that you have a really like really weird taste that is only shared between like you and maybe like 500 other people or something, and then you go to YouTube. Chances are that like in the entire YouTube homepage where they need to insert like a lot of content and compute recommendations for that, there will be a content that is kind of like more like a safe bet from the YouTube side, which is like just more globally popular, right? The content that is streamed or like watched by more people. Some portion of the content can be like really deeply related to like your weird, I don't know, like hobby or something. But still, you would see a lot of content that is really induced by the popularity. So I think in the future, I really look towards a system that can really like deeply understand the user preferences and really tailor recommendation to the specific preference of the user, and maybe like less to the popularity, like the global popularity of the content. So this one I think will be really interesting. And also I think for the new like UXs for the recommendation system, because obviously we have like mobile apps, which are now populated by recommendation system, like pretty much everything when you go to like obviously Instagram, YouTube, Spotify, Netflix, everything is being sent to you by the recommendation system in some form. But it's still an app, right? That you scroll, click, stuff. I'm actually wouldn't be that nice if you would have some kind of like maybe textual experience with the recommendation, like something like ChatGPT, but that also can give you recommendation, and not like hallucinated recommendation, but the one that actually understands the catalog of the system and then gives you an actual like item from this catalog. Better like Amazon recommendations that could always be improved, I think. So yeah, and then those two things, I think.
Yeah, cool. Thank you for this presentation and for this talk and your participation on our webinars. Thank you for all who was with us today. I will be happy to see you all on the next webinars. Don't forget to join to our Discord where we published the recording and the slides. So, and we can continue discussion this topic as well. So thank you for all. See you next time.
Bye. Thanks for having me.
Bye.